All right, hello again. Sorry I can't be with you today, but I want to do two things, and this is the first of those two things. I want to go through some of the homework from section 5.7 using these new integral formulas. And just as a reminder, we don't really have an integral formula for cosine, cotangent, or cosecant. But if you remember the derivative formulas, they were just a negative of each of these. So it happens that I can take anything and write it as a sine, tangent, or secant as far as the integration is concerned. So let me just remind you about a couple of things. This shows up as a squared and u squared. That's significant because what I'm needing is a u. So sometimes I have to kind of piece that apart to be able to find my a and my u. So I want to talk about a couple of these, beginning of the homework problems anyway, beginning with number 3 on page 385. And as always, we want to kind of go through our litany of things to try. Is this even possible to be a du over u case? Well, if it was, I would choose u to be 16 plus x squared, and the du would be a 2x. I don't have an x at all in the top. Then I might even want to try if there's a higher power in the top. We might want to try long division. But we go through all of those things to be able to determine which one is going to work. Integration is not always cut and dry. I have to make it fit the form. And so as I've kind of exhausted all those other rules, I'm certainly left with these three. And I think pretty well all of these are going to fit into one of these three. I don't think that one will be arcsine or arcsecant because of the square root business going on in there. So I think arctangent is going to be it. So let's see if we can't rewrite it in terms of this formula. And the first thing I notice is I've got a 7 in there that I'm not sure I need at all. So I'm going to pull that out. And I can rewrite 16 as 4 squared, and I can rewrite x squared as x quantity squared. And again, what I'm on the lookout for is an a and a u. And so if I choose my u to be x, then my du is just dx. I'm good to go. That fits exactly this arctangent formula. So let's make those substitutions. So I have, that formula says 1 over a. In this problem, a is 4 times the arctan of u over a. So u is x, not x squared. A is 4, not 16. Plus the constant of integration. And again, we want to always clean that up into this thing. So nothing to it. Formula works pretty nice there. Number 5. The integral of 1 over x times the square root of 4x squared minus 1. All right, so again, as I'm looking for one of these formulas, and it's got a square root in the bottom, I believe it's going to be either sine or arcsine or arcsecant. I'm leaning toward arcsecant simply because this has that extra u piece out in front. So let's see if we can't manipulate it and kind of create that that u and a business in there. So let me work under the radical first of all. 4x squared. Well, I can rewrite that as something squared, namely 2x quantity squared minus 1 squared. So then I got to play the u du game, right? So if I'm choosing that to be u, then I have a couple of issues going on. If that's u, then u has to reappear out here. Well, again, u is 2x, so I can fix that. I can put a 2 in and take it out. Keep in mind, we normally put a fraction outside. This is in the denominator is sort of the difference there. And then on my du, the derivative of 2x is a 2 dx. So again, I need a 2 for my du and a 2 out. which works out nice because those are going to cancel out. So this problem is exactly now du over u. And so I can integrate using the arcsecant function, which says 1 over a is 1, so that's just a 1. Arcsecant of u over a, absolute value of u over a. And again, I don't need that 1. Making it fit the form, that's always the name of the game. Number 9. I have 1 over the square root of 1 minus x plus 1 quantity squared. So again, I'm trying to make it kind of fit one of these rules. And the closest one I think it's going to come to is this arc sign. So can I manipulate it and make it look like arc sign? This one doesn't have a u sitting out front. It has a square root, so arctangent's out. So if I choose u to be x plus 1, then the du is 1 dx. I think I'm good there. This looks exactly like a squared minus u squared. So it fits the form for the arc sign. So u over a, x plus 1 over 1. I'm not even going to put the denominator of 1 plus the constant of integration. All right, so again, on all these, we're looking for opportunities to use those 3 formulas. Number 13. Number 13 says e to the 2x, integral rather, of 4 plus e to the 4x. All right, so again, the first thing I'm tempted to try is a u du case. If I choose u to be, or du over u rather, if I choose u to be 4 plus e to the 4x, then the derivative of that is 4e to the 4x. And I don't have a 4x at all up there, so that's not going to work. So let me try one of those trig functions. And so here's those formulas again. I don't have a square root at all, so I think I'll try to make it fit this form. So easily we can make that be something squared. It's this that gets a little tricky. And we want to think again about our properties of exponents and that kind of stuff. So that denominator I can write as 2 squared. And then is there something that I can square? Is there something times itself that would give me e to the 4x? Well, I think e to the 2x squared will do that. And that's nice. And there was kind of a hint to that already because I had an e to the 2x in the problem. So now if I choose u to be e to the 2x, then the du is 2e to the 2x. So I've got everything that I need there. Put my 2 in, take it back out. And now I'll use my arctangent formula. That arctangent formula says 1 over a. That 1/2 is this 1/2. It's still there. 1 over a is a 1/2. Arctan of u over a plus the constant of integration. And we can clean that up slightly. A 1/4 arctan e to the 2x over 2 plus c. Looking again for opportunities to use those formulas. Number 17. Number 17 says the integral of x minus 3 over x squared plus 1. So again, as always, the first thing I'm kind of tempted to try is it a du over u case? Because that integrates nice. So if I choose u to be x squared plus 1, then the du is 2x. Well, great, I've got an x, I could do that, but this 3 is sort of in my way, so I don't think that's going to be a good plan here. So again, we could go through long division, and you can certainly do that on this problem. I'll be honest, it's a little bit quicker just to split the fraction apart. There's one integral. And then here's another integral. So minus 3 x squared plus 1. You don't have to pull that 3 out. I just kind of out of habit used to went ahead and did that. Okay. So now let's see if we can integrate both pieces. Well, again, I kind of pursued this idea a while ago, and I think now it's going to work out for me. I've marked it out, but I'm going to use its result. If I let u be x squared plus 1, then the du is 2x. So that looks exactly like du over u, and I can integrate that into 1/2 natural log x squared plus 1, plus a constant. I'll just hang on to that constant for a moment. And then over here, that looks a lot like this arctangent formula. So let me see if I can't manipulate that and get it to look like that. So if I choose u to be x, then the du is dx. So I think everything's good to go there as well. It already fits the form of u squared plus a squared. So a minus 3 times 1 over a. A in this problem is 1. 1 over 1 is 1. Times 3 is still 3. Arctan of u over a, x over 1. And then I had a constant from this integral. I've got another constant from this integral. Together are both still a constant. I like that kind of problem because I've got to use everything that we've done to be able to answer that question. All of that, the long division business, all of my integral formulas, and so on. So I'm not going to keep going with the other homework problem. They all are real similar to this, perhaps with the exception of number 31. I just didn't want to do the definite integral. But let's look at 31. As always, if you're not sure about those, be sure you're taking advantage of the Learning Lab. So I have the definite integral of dx over x squared minus 2x plus 2, integrating from 0 to 2. So, as always, we go through that whole laundry list of things. If I choose u to be this denominator, I don't think I'm going to be able to get a du there. Right now, it doesn't fit any of my arc function formulas. So, let me just kind of pull over and think about completing the square, which we should have talked about in class. So, think about how completing the square works. We're going to got to have a coefficient of 1 here from algebra, right? Let me just leave myself some room. So we're going to take half of this number. Half of that number is negative 1, and I'm going to square it. Negative 1 squared is positive 1. But again, I can't just go around adding 1's in. I also have to take them back out. So if I pause and I can simplify this line, I get exactly what I started with. But the advantage is, algebraically, all I have force something, this piece anyway, to be a perfect square. Namely, x minus 1 times itself. It'll always factor like that. That's why I completed the square. So I can rewrite that denominator as x minus 1 squared and plus a 1. So back to our problem, I have the integral from 0 to 2 dx over x minus 1 squared plus 1, which I'm going to go ahead and write as an a squared. So this is u squared and a squared. Now, I think this goes without saying, but perhaps it's worth mentioning. My formula is a squared plus u squared, but we know from our work with the commutative property of addition, I can flip-flop those and do u squared plus a squared, which is actually what I have there. If you feel like you need to rewrite that, feel free to. So if I choose u to be x minus 1, then the du is 1 dx. I'm good to go on that problem. So that becomes 1 over a, which is just a 1, arctan of u over a, which is just x minus 1. Again, I don't need the plus c here because it's a definite integral. So that becomes the arctangent of 2 minus 1 minus the arctangent of 0 minus 1. Move my camera over. Sorry, I'm off the page. Which becomes the arctan of 1 minus the arctan of negative 1. And that goes back to that whole conversation and discussion the other day about inverse functions and restrictions. So this ends up being just 45 degrees and a negative 45 degrees in radians, of course, which is 2 pi over 4. The double negative, I add those together, and pi over 2. All right, so any others that we need to talk about, you can do the definite integrals. It's the integration that we're concerned about, of course. We'll deal with those when I return next week.